field of fraction of group ring of fundamental group, roughly speaking, yeah?
Right.
Yeah.
Right. Okay, so that's good. So just some explicit operation on paths. So now to use this to prove the wall crossing formula, we have to do one other thing. We have to understand the role of closed trajectories. So now consider some theta phi 2 where closed trajectory appears. So let me remind you what the picture looked like in that case. So in that case, we had just a single branch point, but it was sitting on a cylinder. It's sitting on a cylinder, and we had S-walls that were winding very many times around the cylinder. All right, I finally lost the brown one, so from now on, the S-walls are orange. So we had an S-wall emerging from here that wound very many times around the cylinder. And eventually it goes up to infinity like this. We had one trajectory that went like this, and then there was a third trajectory that went around the cylinder the other way, and came back like that. So some complicated picture like this on one side, and on the other side, so this is at a phase right before you meet the closed trajectory. And on the other side, there was a very similar picture, except that the roles of the two S-walls had exchanged. So the winding was around this cylinder with the opposite helicity. I showed you computer pictures of this last time, but I didn't draw it by hand. So there's a trajectory that goes down like this. So again, you ask yourself a very similar question. You say, so at the sort of limiting phase, right at the limiting phase, this whole collection of infinitely many windings kind of collapses down onto a single place. And the question is, what happens to, you take a little path that just crosses that critical place, and you ask, how does the f of p for that path jump right when we cross to the critical phase? So here, well, it's a little bit subtle. You should sort of think of this thing as crossing all the infinitely many windings when you get very, very close to the critical phase. So here you have something that crosses, roughly speaking, infinitely many windings here. Here you have something that also crosses infinitely many windings. But those windings are a little bit different. The kind of detours that you're allowed to take are a little bit different. The upshot is you wind up with a very similar transformation. So the only change is, well, maybe it's better to write it like this. So it's 1 plus pi inverse of s plus pi inverse of s squared plus pi inverse of s cubed plus dot dot dot. There's an infinite collection of terms now corresponding to taking detours that wind around arbitrarily many times. So you generate this geometric series here, again to the intersection number of a with pi inverse of s. So then you can rewrite that as 1 minus pi inverse of s, the minus intersection of a with pi inverse of s, a2. So it looks exactly like the thing that we had before, except that there's a minus sign in the exponent, and there's also this tricky little minus sign. Here. So now on passing the traces, what do we get? Well, So now we get gamma goes to gamma times 1 minus gamma s to the minus intersection product of gamma with gamma s, except there's also a 2 here. Why is there a 2 here? It's because these things never come by themselves. They always come in pairs. So if you have one of these, there's always another one. And the intersection, they're represented by the same class in homology. So the intersection products with each of these guys are the same, and so it'll contribute. When you take account of both of them, it'll contribute a 2. So this again. So this was called K gamma s to the minus 2 last time. Okay. So this exactly corresponds to the fact that that saddle connection contributed omega equals +1, and this collection of closed trajectories is supposed to contribute omega equals -2. So now, okay, so from all this stuff, how would you now deduce the wall crossing formula? So now we've done all the necessary work. Well, we've done almost all the necessary work. So now when you return to the picture that we drew last time in stating the wall crossing formula, so the picture was we have the parameter theta, and we have the parameter u in the space of quadratic differentials, the parameter space of all quadratic differentials. And on this picture, we drew lines corresponding to the places where the various special trajectories occurred. And to each one of those lines, we attach some transformation. So here I would attach K gamma to the omega of gamma. Here I attach K gamma prime to the omega of gamma prime, and so on. And what the wall crossing formula said was that if you go around some loop, well, if you go around some square loop, say, if you draw some square loop like this, that the composition of the transformations that you get here, this transformation times this transformation, is the same as the composition of the transformations you get here, say this one times this one times this one, or whatever it should be, some product of these K's. So now you see the point. We've actually constructed some objects. We've constructed some actual objects, namely these T of P's, whose transformation at these loci is exactly given by these transformations. On the other hand, these T of P's are defined in a sort of univalent way. So what you get, the transformation that you get by taking this path and the transformation that you get by this path have to be the same because they lead you to the same T of P in the end. So what this shows is that the compositions, I think we called this composition last time S of theta, theta prime, and U. This was U, U prime, theta, and theta prime. So the compositions S of theta, theta prime U, and S of theta, theta prime U prime, this composition and this composition, at least you can say they act the same on all of these T of P's, almost by definition. So these T of P's are objects that live inside this the group ring of the homology of the surface, of the covering rather. And what we're saying is that in there's a bunch of objects T of P inside that group ring. There's a bunch of objects T of P which are invariant under the difference of these two things. So that's almost enough to prove the wall crossing formula. What you would need to prove the wall crossing formula is to know in some sense there's enough of these T of P's that they kind of generate the whole group ring. So for that,
Can you repeat why it's so obvious that at this level there is already an identity?
it's just because So what we've done is we've defined some objects T of P, which are defined they depend on the extra data of a point on this picture. But they're defined in a unique way. They depend only on that point, not on some path reaching that point. And on the other hand, we know how they jump.
Okay.
At the wall. So just explicitly, since you reach the same object here, you have to have reached it by
You
the
claim
same.
that it's because they are well defined.
Just because they're well-defined objects, yeah, exactly. So at least we know that these transformations act the same on all T of P. And so now what we need to know is that there's kind of a lot of T of Ps. That they are sort of, well, certainly it would be enough to know that they generate this this homology. So to conclude that T of P, that S of U, S of theta, theta prime and U equals S of theta, theta prime and U prime, we need to know there are enough T of P's. And so this part, unfortunately, so it's true, you can prove it, for example, using the technology of Fak and Goncharov. But I don't have a super conceptual way of saying it. So at least for today, I want to avoid this part. So we've come far enough to see that the wall-crossing formula holds at least when it acts on some restricted subset of, at least when it acts on the T of P. So can do this. So you can sort of construct enough T of P using results of Fak and Goncharov. But at least for now, let me not say more about that part. So I've sort of almost explained the proof of the wall-crossing formula to you, but I haven't completely explained it. I've only shown you the identity modulo of this statement. So now I want to turn to something else. So in trying to understand this wall-crossing formula, we've been led to this kind of funny-looking construction. This construction where you take paths and you take paths on C and you lift them up to the covering. And that construction seems to have a lot of other uses. So I want to describe sort of one of its other uses.
Just one question before that. If you consider some non-trivial loop in the space of quadratic differentials, would be the total birotional transformation trivial?
If it's not contractible, if it's not contractible in the base,
Yeah. Maybe so.
You mean if it goes around one that has like a double zero or something?
Yeah, or you go around theta circle, for example.
If you go around the theta circle, in the case, that depends on what kind of singularities you took. So if we took just second order poles,
Yeah.
oh no, in fact, even if we didn't take just second order poles, sorry. Yes, it's true.
It's true.
Yeah. I mean, after all, the thing was really well defined.
Nice.
Yeah. That's right. Okay. So now I want to talk about flat connections. So another use. Another use of the path construction. So it gives a relation between GL1 connections. In other words, connections on rank 1 vector bundles on sigma. So on the one hand, rank 1 connections on the covering space sigma, and on the other hand, GL2 connections, so connections on rank 2 bundles, on C. So how does that work? So it's a kind of like a Booleanization or non-Booleanization, depending on which way you run it. Actually, the way that we run it, it will most directly be the non-Booleanization. So what's the idea? So say we have a rank 1 connection, GL1 connection, which I'll call nabla Boolean. Connection on a rank 1 vector bundle on C. And suppose that I would like to make a rank 2 connection on C downstairs. Well, what could I do? So the most obvious thing you could try to do is just take the direct image, right? We've got this double cover, so it's got some line bundle over it. Let's call it L. So locally, I've got say sheet 1 and sheet 2 here. So I could try to define. I could define a vector bundle downstairs to be just a push forward. So its projection again is pi. I could define it to be just the push forward of L. So locally away from the branch points of the covering, it would just be a direct sum of 2 lines, L1 plus L2, namely the fiber of the bundle here and the fiber of the bundle here. But that's an obvious way of constructing a rank 2 bundle. And moreover, of course, it looks good. It looks like it comes with a connection, right? Because after all, I have a connection in the line bundle L. So each of these lines has a connection in it, and so I could just make the diagonal connection, right? So this is sort of canonically equipped with the diagonal connection. So if you like, I'll call it nabla abelian 1 direct sum nabla abelian. Right, you just have a sum of 2 lines, so I just have the most trivial possible connection. So okay, well, actually this is only away from the branch points. It's away from the branch points, but you might think, well, there'll be some way to fill it in over the branch points and there won't be a problem. But actually there is a problem, and you can see the problem if you just take this connection and calculate its monodromy around one of the branch points. So suppose I take this sort of naive direct sum connection. Suppose I take this naive direct sum connection, I take monodromy around one of the branch points. So monodromy of nabla around a branch point. Well, in some local trivialization, it looks unfortunately like this, because it just exchanges the 2 sheets, right? It exchanges L1 and L2. So that's bad news if you're trying to make a flat connection over the whole curve C, right? There's going to be no way of filling it in because it has this monodrome. So you might think, okay, well this is just dead. There's no way of doing it. But actually, this path lifting construction that we gave is exactly the gadget that helps you to fix this problem. So we need to improve this construction. Okay, let's try again. So what do I need to do in order to define a connection? What I have to do is I have to define the parallel transport operator between any 2 points, right? So if I have that compatibly with composition, it's the same as having a connection. Sorry, if I have that with homotopy invariance and compatible with composition, it's the same as having a connection. Well, those are exactly the properties that my path lifting thing had. So we'll specify, so for any path P on C, we'll give an element, let's call it H(P) in the Hom space, in the Hom from E, let's see, P goes from, say, Z1 to Z2, P from Z1 to Z2, we'll give an element H(P) in the Hom from the fiber EZ1 to EZ2. So we're not going to change the bundle. The bundle is still going to be this push-forward bundle. We're just going to change the connection length. And what is it? Well, what we do is we take our path and we look at its lifted version. So here's the construction. So L of P is some sum with coefficients Ci of paths. Let's see. Let's call them alpha. Let's call the coefficients alpha I. So these are some integers, and these are paths on sigma. So I take my path P, I lift it up to some sum of things here, and now we'll define H(P) to be just the sum now of the parallel transport. I use the parallel transport of the abelian connection along each of these paths upstairs. So it's the sum, again with the same coefficients alpha I. So now I'll take the whole of the abelian, the parallel transport of the abelian connection upstairs. So this H(E.S) is the parallel transport of our abelian connection, which I guess I called nabla E. So what does it mean? Well, so for short paths, it means exactly what it meant. It's exactly the naive thing, right? So if I have a path that doesn't cross any S walls, so if P doesn't cross any S walls, then L of P is just P1 plus P2, right? The two lifts of it upstairs. So this is on C, this is on sigma. So for short paths that don't cross any S walls, we just have this, and in that case, this operation just means you take the sum of the two parallel transports in the two separate lines. In other words, it's exactly the diagonal connection. So here, H(P) is just the whole the parallel transport. The parallel transport of the push forward connection. But for a path which crosses one of the S walls, we're modifying it. We're adding some terms, and those extra terms exactly have the effect of sort of non-abelianizing the connection, right? Because we have the thing decomposed into two lines, but these extra detours connect one line to the other. For P which crosses an S wall, one or more S wall, H(P) is not the thing that would come from just taking push forward not lab. But that's good because that thing had a monodromy, and our thing has. So now we've constructed it so that it actually doesn't have a monodromy.
But don't you need to define the monodromy along the path which turns around the subtle connection?
Well, no, this path lifting rule was a totally uniform rule, right? It works for every path. I mean, the rule was more or less complicated depending on which path, because sometimes you have to take some detours, sometimes you don't have to take some detours, but no, we've defined it for every path, and so now we have a holonomial operator for every path that gives you a flat connection. Okay, up to one subtlety that I suppressed so far, so maybe this is the thing you're thinking about. It's true that this thing, to be honest, right, when I said it, this thing wasn't exactly homotopy invariant. It had this twisting in it. It had these tricky signs. So is that what you're worried about, or something else?
No,
Okay, so
At least I would like to ask about the size.
oh, okay, okay. So indeed, so strictly speaking, what we construct in this way is not exactly, it's almost a flat connection, but it has a little twist. So let me explain exactly what it is. Okay, so
Sorry, but how about the continuity? Like, as you have a small path which moves a little bit, and then at some point it hits an S wall.
that's fine.
And then you move over. So doesn't it suddenly acquire something?
Yes. That's right. Yeah. Sorry, you're right. I slightly cheated when I said that the bundle is. You're right. Sorry. So yeah, if I think of it as being a connection on exactly the original bundle push forward of L, then I have the kind of then I'm into the kind of problem you're describing. So sorry. Let me say it more accurately. In the regions away from the walls, in each region away from the wall, the thing is isomorphic to the push forward of L. So on the complement, so here, and here, the thing is isomorphic to the push forward of L. Now at the walls, you're actually gluing together those copies of the push forward of L by some non-trivial matrix. So once you've included that gluing, the parallel transport operator is really continuous. Let me say it another way. In case that leaves you with some sort of lingering concern. So one way of thinking about what a vector bundle, with connection is it's just a functor from the groupoid of all paths on the curve C, a functor from there to the category of vector spaces. So I just have to assign to every point here a vector space, and to every path I have to assign a map between the vector spaces. So here I'm just doing it point-wise. So I'm assigning to every point I'm assigning the direct sum of the fibers of L over that point, and to every path I'm assigning just this sum of polynomial operators that I wrote up there.
And so strictly you're doing that at all points except the zeros, and then claiming that the monotony around the zeros is the identity.
Right, that's right. I'm not giving you the construction at the zeros, but because the monotony around the zeros is the identity, it has to fill in also over the identity.
You will get metric something like 0, 1, minus 1, 1? Or?
No, we're never going to meet that. The gluing, the gluings across here? Yeah, if you try to write the gluings explicitly, what they look like is something like this. So
No. I think it's more out there. It should be cubic root of identities. Yeah, it was 0, 1, minus 1, minus 1, I think
it depends on your. I think I know what identity you have in mind. So it depends a little bit on your local trivialization, but here's the identity that might satisfy you. So.
sounds like this.
So what it says is, if I have three sort of upper triangular monodromies like that, and I glue them together, then I can eliminate up to the tricky signs which come from the twisting. I can eliminate the monodrome medium. So no. Once this is so you can think of it, if you like, as having this push forward of L along each patch, and then you're gluing them together by some explicit transformation. But in the end, the thing is really smooth. So it's really an honest to God flat connection, flat SL2, flat rank 2 connection over C.
And it really is flat. The signs get eaten up.
Okay, right. So there's minus signs. Okay, good. So sorry. Yeah. So there is the subtlety of the minus sign. So the more exact statement.
It's PSL. What you constructed is PSL already.
One thing you could do is go to PSL, but there's something a little sharper I can say.
Jail is really perfect. Jail version is really the best.
So more precisely, what we constructed a map from twisted local systems, I'll have to say what a twisted local system is up here. The twisted flat connections, flat GL1 connections on sigma to twisted flat GL2 connections on C. And what do I mean by twisted? So a twisted local system on S, so for S any surface. Sorry, twisted flat connection. Is a flat connection, so it's actually not a flat connection on S, it's a flat connection on the unit tangent bundle to S. So that was what I called, I had C twiddle and sigma twiddle before. We talked about the lifts of paths to the unit tangent bundle. So it's a flat connection on S twiddle. Now, if we had a flat connection on S twiddle with monodromy 1 around the fiber, that would be just the same as having a flat connection on S. But here we take a flat connection on S with monodromy -1 on the fiber, on any fiber of S twiddle. So it says exactly that if I rotate around the tangent vector by 360 degrees, this connection has monodromy -1 rather than the 1 that you would expect. Now, this isn't too far off from being a flat connection. So for example, if you choose a spin structure on S, then you can canonically identify the space of flat connections with the space of twisted flat connections. The easiest way to see it is that a spin structure gives you a double cover of S twiddle, a fiber-wise double cover of S twiddle. So if you have a connection on S twiddle with this property, you just lift it to the double cover, then it has monodromy 1, and then it descends to an honest flat connection on S. So
the same as to talk about twisted DT modules.
It's the same as talking, okay, I believe that it's the same as talking about D modules that are twisted by k to the 1/2. And that's a twisting that, as you know, comes up a lot in that. So it's somehow a very canonical thing. I mean, I think the D modules people would say this is more natural than an honest flat connection. Anyway, this is what you get on the nose. I just don't think there's a version of this construction which does it for the untwisted ones, at least not without making some arbitrary choices.
No, in fact, we have such a contour for JLN without any.
Oh, you have it without the
without
twisted?
distances.
Okay, so then so anyway, I got the twisted. What I got was most naturally the twisted version.
I'm sorry, I don't understand still about this question of continuity. So does the twisting take care of that when you go there?
No, the twisting has nothing to do with this problem of continuity.
But is there continuity or not when we change the parameter space?
It is, sorry, which, the parameter space or the?
Quadratic differential. I mean,
Oh, changing the quadratic differential is another question. So
but it's continuous when we change the quadratic differential?
it's continuous until you reach these walls.
So it's not continuous. So the answer to the question.
No. Oh, I thought the question was a different question.
It was different.
It was different.
Yeah. Yeah. The answer to that question was that the thing is continuous, although it allows you to have it. Okay, so let me take a break there, and then I'll start on the higher ranked version.